November 15, 1943. Aberdeen Proving Ground, Maryland, 70 miles northeast of Washington, D.C. Major Thomas Doane stood in the observation bunker watching the 15th Sherman tank of the day take direct hits from a captured German 88mm anti-tank gun, and what he witnessed made his stomach turn, even though he'd been observing these tests for 3 weeks and should have been numb to the results by now. The 80mm round penetrated the Sherman's side sponson, where ammunition was stored in racks that had no special protection beyond the tank's basic armor, and within seconds flames erupted from every hatch and Vision Porter's ammunition cooked off in a cascading chain reaction that turned the 33-ton vehicle into an incinerator. That would kill any crew still trapped inside. Doane had commanded a tank company in North Africa, had seen Shermans brew up exactly like this when hit by German fire, had pulled charred bodies from burned-out hulls, and had written letters to families explaining that their sons or husbands had died instantly, even when he knew they'd probably burned alive screaming, for help that couldn't reach them through fire and smoke. That made rescue impossible. The testing program at Aberdeen was supposed to identify solutions to this catastrophic vulnerability. That was killing American tank crews at rates that would have triggered congressional investigations if the details weren't classified, but 3 weeks of systematic testing had produced nothing but confirmation that the Sherman's ammunition stowage design was fundamentally flawed and that every proposed fix either didn't work or created new problems that made the tank less combat effective. Around him in the bunker stood representatives from Army Ordnance Department, from the various manufacturers producing Sherman variants, from Army ground forces, who would have to employ whatever solution emerged from this testing, and from the office of Lieutenant General Leslie McNair, who'd spent 2 years insisting that American tank doctrine didn't require heavily armored vehicles because tank destroyers would handle enemy armor, while Shermans supported infantry and exploited breakthroughs. What Doane didn't know, what none of the 50 men observing today's tests could have anticipated as they watched another Sherman burn, was that sitting in the back row of the observation bunker was a civilian engineer named Harold Cole from the Fisher Body Division of General Motors, who'd been assigned to Aberdeen 3 months earlier to assist with testing, but who'd spent his evenings working on a radical ammunition stowage redesign that Army Ordnance had already rejected twice as impractical and too expensive to implement given production schedules that couldn't be disrupted without delaying the build-up of American armored forces in England for the invasion everyone knew was coming in. 1944. Within 6 months, Cole's rejected design would be adopted as standard for all new Sherman production, despite institutional resistance that had nearly buried the concept, would reduce the rate of catastrophic ammunition fires from 80% to 15% in tanks equipped with the new system, would save thousands of American lives in the fighting from Normandy through Germany, and would represent one of the most significant engineering improvements to emerge from systematic battlefield analysis during World War II. The story of how a mid-level engineer's persistence overcame military bureaucracy and manufacturing resistance illustrates both the capacity of American industrial system to innovate under pressure and the tragic cost of institutional inertia that delayed critical improvements until after thousands of men had died in tanks that could have been made survivable months earlier if different decisions had been made by officers who prioritized production, numbers over crew protection. The story of how Sherman tanks became death traps for their crews begins 2 years earlier in 1941 when American tank designers were racing to create a medium tank that could match German Panzers while being simple enough to mass produce in quantities that would compensate for America's late entry into armored warfare development. The Sherman evolved from the M3 Lee, a stopgap design that mounted its main gun in a hull sponson because American designers hadn't yet figured out how to build a reliable turret large enough for a 75mm gun, and the urgency of getting tanks into production meant that compromises were made in dozens of areas where more time would have produced better solutions. But time was the one resource America didn't have in 1941, with German panzers dominating European battlefields and Japanese forces preparing for expansion across the Pacific. The original Sherman design placed ammunition throughout the vehicle wherever space could be found. Sponson racks on both sides of the hull above the tracks where crew could access rounds easily, but where enemy fire would penetrate the relatively thin side armor and directly impact ammunition. Ready racks around the base of the turret basket, where loader could reach rounds quickly, but where any penetration of the turret ring area would ignite them. Floor racks that were better protected by being low in the hull, but harder to access during combat. And scattered storage in every available space because a Sherman carried between 90 and 100 main gun rounds, depending on variant and finding room for that much. Ammunition in a vehicle designed for 5 men, and all their equipment required, using every cubic foot of internal volume. The engineers at Rock Island Arsenal, who designed the Sherman's internal layout, understood that ammunition stowage near the sides of the tank was dangerous, but they faced competing requirements that seemed impossible to reconcile. Crews needed quick access to ammunition during combat, which meant placing it near the loader's position in the turret. But the safest location for ammunition was low in the hull center, where it was most protected by armor and distance from potential penetration points. And these two requirements were fundamentally incompatible given the Sherman's internal geometry and the amount of ammunition it needed to carry. The compromise was ammunition stored in multiple locations with some emphasis on sponson racks that proved catastrophically vulnerable once Shermans started, encountering German tanks with high-velocity guns that could penetrate American armor at ranges where Sherman crews couldn't effectively return fire. When the first Shermans entered combat in North Africa in late 1942, at the Second Battle of El Alamein, they performed well against German Panzer III and early Panzer IV models that had relatively weak guns and whose armor the Sherman's 75 mm could penetrate at reasonable combat ranges. But by mid-1943, the Germans had upgunned their Panzer IVs with long-barreled 75 mm guns and had introduced the Tiger I with its 88 mm gun that could penetrate a Sherman's front armor at 2,000 yards, while the Sherman had to close to under 500 yards for any chance of a frontal penetration. And suddenly American tank crews were dying at rates that suggested fundamental design problems rather than normal combat attrition. The casualty reports from Tunisia and Sicily in 1943 painted a grim picture that Army ordnance could no longer ignore even if they wanted to. Shermans that took penetrating hits burned at rates approaching 80%, and crews that survived the initial penetration often died in the fires, because the ammunition cook-off was so rapid they couldn't evacuate before flames consumed the interior. British tank crews who received Shermans through Lend-Lease started calling them Ronsons, after a cigarette lighter, whose advertising slogan was "Lights the first time, every time." And while the nickname probably emerged from British dark humor rather than German usage as sometimes claimed, the fact that crews were making jokes about their tanks burning illustrated how pervasive the problem had become. German tank crews reported that they didn't consider a Sherman destroyed until it was burning because American recovery and repair capabilities were so efficient that a merely immobilized Sherman would often be recovered and returned to service within days. So German doctrine emphasized continuing to fire at disabled Shermans until ammunition fires made them total losses. American armor officers from units that had fought in North Africa and Sicily reported that tank crews were experiencing psychological trauma from watching friends burn to death in vehicles identical to their own, that some crews were refusing to load full ammunition complements in hopes that carrying fewer rounds would reduce fire risk, even though this made them less combat effective, and that the tanker replacement system was struggling to find volunteers willing to crew Shermans after veterans rotated home and told realistic stories about what tank combat actually involved. Major General Jacob Devers, who commanded American armored forces before moving to the European theater, pushed Army ordnance to address the Sherman's vulnerability, arguing that improved armor and ammunition protection were critical if American tanks were going to face the newer German tanks intelligence reports indicated were entering production. But Devers' advocacy ran into the institutional reality that fixing the Sherman's design flaws would require either accepting reduced production while factories retooled for changes or allocating resources to develop new tank designs that wouldn't enter service for months or years, and neither option was acceptable to senior Army leadership, who believed that winning the war required getting maximum numbers of adequate tanks into combat, rather than smaller numbers of superior tanks that would arrive too late to effect crucial battles. Lieutenant General Leslie McNair embodied this production over quality philosophy through his tank destroyer doctrine that treated American tanks as infantry, support and exploitation vehicles, while specialized tank destroyers would handle enemy armor, which meant, in McNair's view, the Sherman didn't need heavier armor or better ammunition protection because it shouldn't be fighting other tanks anyway. The logical flaw in this doctrine became apparent in combat, where enemy tanks didn't cooperate with American tactical theory and frequently engaged Shermans, regardless of whether that fit McNair's preferred division of labor. But institutional inertia and McNair's bureaucratic power meant his doctrine shaped American tank development through 1943, despite mounting evidence that it was getting tankers killed unnecessarily. By fall 1943, when the testing program at Aberdeen Proving Ground was examining solutions to the Sherman fire problem, Army Ordnance had already tried several approaches that either hadn't worked or had produced only marginal improvements that didn't justify the production disruption required to implement them. The first attempted fix was welding 1-inch thick applique armor plates to the outside of the sponsons over the ammunition racks, theory being that this extra armor would prevent penetrations from reaching the ammunition, or at least reduce the number of rounds that detonated by containing some of the fragments from penetrating shells. Testing showed this applique armor did almost nothing because high-velocity anti-tank rounds that could penetrate the Sherman's side armor weren't meaningfully slowed by an additional inch of steel. And even when the applique plates prevented direct penetration, the spalling effect, where fragments broke off the inside of armor and ricocheted through the crew compartment, meant ammunition was still being hit by metal fragments hot enough to ignite propellant. The second approach was redesigning ammunition containers to be more fire-resistant by using steel boxes with better seals instead of the canvas or thin metal containers originally used. But this modification added weight and volume without significantly improving fire resistance, because once a high-explosive or armor-piercing round detonated inside a Sherman, the overpressure and fragments would breach any reasonably sized container. Some units experimented with removing ammunition from sponson racks and storing it all on the floor, accepting the inconvenience of the loader having to bend down to retrieve rounds during combat. But this field modification was inconsistently applied and didn't solve the fundamental problem that a Sherman hit in the side would often have its ammunition ignited, regardless of where exactly that ammunition was located. The testing at Aberdeen was supposed to be systematic and comprehensive, examining every possible modification and measuring its effectiveness against captured German weapons that represented what Shermans would face in combat. But by mid-November, the testing had mostly confirmed what pessimists already suspected. The Sherman's basic layout made it inherently vulnerable to ammunition fires, and any real solution would require major redesign that would disrupt production and delay the massive buildup of American armored forces in England that was already behind schedule. Major Doane had been arguing for weeks that reducing ammunition load from 90-plus rounds to 60 or 70 would significantly reduce fire risk, since fewer rounds meant less chance of catastrophic cook-off. But this proposal was rejected by senior officers, who insisted that tanks needed maximum ammunition for sustained combat, and that reducing loadout would compromise operational effectiveness. The bureaucratic impasse was frustrating everyone involved, because the technical problem was obvious and the human cost was mounting, with every engagement in Italy where American armored divisions were discovering that German defensive positions employed the new Panther tanks, whose 75mm guns outranged and outpenetrated anything the Americans could field, creating kill ratios that would have ended armored operations if American numerical superiority hadn't allowed replacement of losses faster than Germans could inflict them. Harold Cole had been working for Fisher Body Division of General Motors for 11 years when he was assigned to the Aberdeen testing program in August 1943, part of a liaison arrangement where manufacturers sent technical representatives to Army facilities to provide expertise and to learn what combat experience suggested about needed design improvements. Cole was 41 years old, had studied mechanical engineering at Michigan Agricultural College before the institution became Michigan State, had worked his way up from draftsman to senior designer by demonstrating unusual ability to visualize three-dimensional mechanical problems and find elegant solutions that other engineers missed because they were thinking conventionally. His assignment at Aberdeen was supposed to be temporary, 3 months observing testing and reporting back to Fisher Body about modifications that might be required in their Sherman production lines. But Cole had become increasingly obsessed with the ammunition fire problem as he watched tank after tank brew up during tests and realized that the solutions being discussed were all variations on the same flawed approach of trying to protect ammunition in its current locations rather than completely rethinking where ammunition should be stored. The insight that would eventually revolutionize Sherman's survivability came to Cole during a test in late September when he watched a Sherman take a hit low in the hull that penetrated below the sponson and tore through the floor without igniting ammunition, and he realized that rounds stored at floor level or below were protected by distance from the most likely penetration points and by the mechanical components and fuel tanks that surrounded the lower hull and acted as additional barriers between enemy fire and ammunition. Cole spent 3 evenings sketching concepts for moving all main gun ammunition to the floor of the hull in the center of the tank, between the transmission in front and the engine in rear, creating racks that would hold rounds vertically in containers below the turret basket, where they'd be protected by the thickest armor and by distance from the sides of the tank where most penetrations occurred. The design was radical because it required eliminating the sponson racks entirely and relocating 70-plus rounds to space that was currently occupied by turret basket supports and crew equipment storage, which meant redesigning the turret basket to be suspended from the turret ring rather than supported by the floor, and relocating dozens of items that crews needed access to during operations. Cole brought his sketches to Major Doan, who was intrigued but skeptical about whether the design could work given space constraints and the need for the loader to access ammunition quickly during combat. And Doan passed the concept to Ordnance Department representatives, who rejected it almost immediately on grounds that it would require extensive retooling of production lines and that the suspended turret basket design was mechanically questionable and might fail under the stress of rough terrain and combat vibrations. Cole's design was officially rejected in early October with a perfunctory note thanking him for his input, and he was told to focus on his assigned role of observing tests rather than designing alternative solutions. But Cole couldn't let go of the concept because he'd done enough calculations to convince himself that the weight and space requirements could be managed and that the suspended turret basket would actually be more reliable than the existing design because it would eliminate several potential failure points where the floor-supported basket could bind or crack under uneven loads. What happened next illustrates both the best and worst aspects of American military-industrial cooperation during World War II. Because Cole's response to having his design rejected was to continue working on it without authorization during evenings and weekends, refining the calculations and creating detailed engineering drawings that addressed every objection the Ordnance Department had raised, while simultaneously the mounting casualties in Italy were creating political pressure that would eventually force reconsideration of solutions that had been dismissed as too difficult or expensive to implement. Cole's unauthorized work violated the terms of his liaison assignment, which specified he was supposed to observe and report rather than independently develop designs. But he rationalized this insubordination by telling himself he was doing it on his own time, and that if his calculations proved the design was practical, he could present it again through proper channels with enough supporting documentation to overcome bureaucratic resistance. The key innovation Cole developed during October and November 1943 was adding water jackets around the ammunition containers, surrounding each rack of shells with glycerin water solution that would absorb heat from any fragments or fire that reached the ammunition and would theoretically prevent propellant from reaching ignition temperature, even if the containers themselves were breached by penetrating rounds or spalling fragments. The concept wasn't entirely original. Naval vessels had used water cooling for magazine protection since the late 19th century, and some armored vehicle designers had proposed similar systems in the 1930s. But Cole was the first to create practical implementation that could fit within a Sherman's limited internal volume, and that wouldn't add so much weight that it compromised the tank's already marginal power-to-weight ratio. His calculations showed that a glycerin-water mixture in containers totaling approximately 100 gallons could surround ammunition stored in floor racks and would provide enough thermal mass to prevent ignition for the critical first seconds after a penetration, when fires either developed into catastrophic cook-offs or could be suppressed by crew action and automatic systems. The glycerin addition was crucial because pure water would freeze in cold weather and would boil too quickly under combat conditions, while glycerin raised the boiling point and prevented freezing while maintaining the thermal absorption properties that made the system effective. Cole's detailed drawings showed how the ammunition racks could be redesigned as sealed containers, with double walls creating cavities for the glycerin water solution, how these racks could be installed in the hull floor between existing structural members without requiring major redesign of the Sherman's basic architecture, how the turret basket could be suspended from strengthened turret ring bearings rather than supported by hull floor, thus creating space for the floor ammunition storage, and how the system would actually simplify ammunition handling, because all rounds would be stored in one standardized location, rather than scattered throughout the vehicle in different rack types. By late November, when the Aberdeen testing program was concluding with a pessimistic report that no practical solution to the Sherman fire problem could be implemented without major production delays, Cole had a complete design package that he believed answered every objection and that he was determined to present through whatever channels would listen, even if it meant going outside the military bureaucracy, to congressmen or journalists who might force official reconsideration through public pressure. The personal risk Cole was taking by continuing this unauthorized work was significant because defense contractors during wartime operated under strict security protocols, and unauthorized design work could be interpreted as exceeding his clearance or as attempting to profit from proprietary information. But Cole had become so obsessed with solving the problem after watching so many test tanks burn that he was willing to risk his career and potentially face legal consequences if it meant getting a solution implemented that would save American lives. The opportunity Cole needed came in early December 1943 when Major General Gladian Barnes, Chief of Army Ordnance Research and Development, visited Aberdeen to review the testing program results and to explain to a skeptical group of field officers why the Ordnance Department couldn't immediately fix the Sherman's vulnerabilities without compromising production schedules. Barnes had been catching political heat from multiple directions. Combat commanders in Italy were sending increasingly urgent reports about Sherman losses and crew casualties. General Dwight Eisenhower's staff in England was expressing concern about whether Sherman-equipped armored divisions could successfully fight through French hedgerow country, where engagement ranges would be short and German defensive positions could employ their superior anti-tank guns with devastating effect, and Congressional Armed Services Committee members were asking pointed questions about why American tanks seemed inferior to German designs, despite America's industrial superiority. Barnes was sophisticated enough to understand that telling Congress, "We can't fix the problem without disrupting production," was answer that might be technically correct but was politically unacceptable if casualties continued mounting, and he'd come to Aberdeen hoping to find some modification that could be implemented quickly enough to demonstrate responsiveness to field complaints, even if it wasn't a complete solution. Major Doane, who'd been impressed by Cole's earlier sketches despite the official rejection, arranged for Cole to have 15 minutes with Barnes to present his wet stowage concept, gambling that Barnes might be receptive to innovative thinking if the presentation was professional enough and if the design addressed practical implementation concerns that had doomed earlier proposals. Cole's presentation on December 8, 1943, was the most important 15 minutes of his professional life, and he'd prepared obsessively for days, creating a scale model of the wet stowage system from wood and metal that demonstrated how components would fit together. Preparing calculations showing weight increases would be manageable and wouldn't significantly affect Sherman performance. Bringing photographs from the Aberdeen tests showing where penetrations typically occurred and how his floor-mounted ammunition storage would be protected by distance and by intervening components from those most common hit locations. Barnes asked tough questions about production implementation, about whether Fisher Body and the other Sherman manufacturers could retool quickly enough to meet invasion timelines, about whether the glycerin water system would require maintenance that would burden field units already struggling with mechanical reliability issues on tanks operating under harsh conditions, about whether the system would actually work under combat stress or would fail in unpredictable ways that might make things worse rather than better. Cole answered each question with specific technical details and with refreshing honesty about uncertainties, acknowledging he couldn't guarantee the system would reduce fire rates to near zero, but presenting data suggesting it should achieve 70 to 80% reduction based on thermal calculations and basic physics of heat absorption, which would represent massive improvement over current 80% burn rate, even if it wasn't perfect solution. What apparently convinced Barnes was Cole's point that the wet stowage system could be implemented incrementally. New production tanks could be built with the system from the start once manufacturers retooled, but existing tanks in inventory or already deployed could be retrofitted with simplified versions that would still provide significant protection improvement even if not quite as effective as purpose-built installations, meaning the fix could begin showing results within months rather than requiring complete fleet replacement that would take years. Barnes also recognized that the wet stowage concept addressed a criticism that was becoming increasingly difficult to deflect, which was that American tank designers seemed unwilling to learn from combat experience and continued producing vehicles based on pre-war doctrine that battlefield reality had proven inadequate. The Sherman's ammunition fire vulnerability had become symbol of broader institutional failure to adapt quickly to combat lessons, and Barnes understood that implementing Cole's design would demonstrate Army Ordnance's responsiveness to field concerns even if it came later than it should have, which was better than the alternative of continuing to insist that no practical solution existed, while casualties mounted and morale among armored units deteriorated. The meeting lasted 45 minutes instead of the scheduled 15, and when it concluded, Barnes had authorized immediate prototype development, with instructions that cost and production schedule concerns were secondary to proving whether the concept would work, which represented dramatic shift from the cost-benefit analysis that had dominated earlier discussions about Sherman improvements. Barnes authorized a prototype wet stowage Sherman to be built at Aberdeen with Fisher Body engineers, working directly with Army Ordnance specialists, gave the project 60 days to produce a testable vehicle, and made clear that if testing confirmed Cole's claims, the system would be approved for immediate production implementation, regardless of how loudly manufacturers complained about retooling costs and schedule disruptions. The prototype construction in December 1943 and January 1944 revealed numerous practical problems that Cole's paper design hadn't fully anticipated, but that competent engineering could solve through iteration and compromise. The glycerin water containers needed special seals to prevent leakage during the vibration and shock of off-road movement. The ammunition racks required redesign several times to achieve proper fit while maintaining structural strength. The turret basket suspension system needed heavier bearings than originally calculated because combat loading of equipment and supplies created asymmetric weights that Cole's theoretical analysis hadn't adequately modeled, and the whole system added approximately 1,200 pounds to the Sherman's weight, which required minor adjustments to suspension and transmission to maintain performance specifications. The engineering team working on the prototype included not just Cole and other Fisher Body personnel but also representatives from Chrysler and Pressed Steel Car Company, who were major Sherman producers and who needed to understand the system well enough to implement it in their own production lines, and this multi-manufacturer collaboration helped identify potential production problems early enough that solutions could be incorporated into the year. Final design, rather than discovered after factories, had already begun retooling. One particularly difficult problem involved the ammunition loading process, because moving all main gun rounds to floor storage meant the loader had to bend down repeatedly to retrieve shells during combat, which testing showed was slower and more fatiguing than accessing ammunition from sponson racks at waist level, potentially reducing the Sherman's rate of fire enough to offset the survivability improvement by making it less combat effective. The solution involved redesigning the floor racks with spring-loaded platforms that kept the topmost rounds at a height the loader could reach without excessive bending, with rounds automatically rising as upper ones were removed, similar to mechanisms used in some machine gun ammunition feeds. This addition complicated the design and added weight and cost, but testing showed it maintained acceptable loading speeds while preserving the protection benefits of floor storage, representing the kind of practical engineering refinement that separated theoretical concepts from systems that would actually work under combat conditions. By late January, the prototype was ready for testing against the same German 80mm gun that had destroyed so many Shermans during the previous months of evaluation, and the results exceeded even Cole's optimistic predictions. The wet stowage prototype took 5 penetrating hits in locations that would have certainly caused ammunition fires in standard Shermans, and in none of those 5 tests did ammunition ignite, with post-test inspection showing that while the glycerin water containers had been breached by fragments and some solution had leaked out, enough remained around the ammunition to prevent propellant from reaching ignition temperature, despite the thermal shock of penetration. The most dramatic test occurred on January 28th, when an 80 bare meters round penetrated the hull side in a location that would have hit sponson ammunition racks in a standard Sherman, but instead passed between the wet stowage containers in the floor without breaching them. And even though fragments from the penetration created multiple small holes in the container walls, the ammunition remained cool enough to handle safely when inspectors examined the interior after the test. Additional testing examined whether the wet stowage system would fail in ways that might endanger crews, whether, for example, the glycerin water solution might itself become dangerous if heated, or if the containers might rupture catastrophically under certain hit conditions. But these concerns proved largely unfounded, with testing showing the system failed gracefully when overwhelmed rather than creating new hazards. Major Doan reported to Barnes that while 5 tests wasn't statistically definitive, it was enough to justify immediate production approval given the urgent operational need. And Barnes agreed, issuing orders in early February 1944 that all new Sherman production would incorporate wet stowage, beginning no later than April 1st, and that retrofit kits would be designed for field installation on existing tanks with priority, given to units preparing for the Normandy invasion. The speed with which this decision was implemented once Barnes committed to it demonstrates what American industrial mobilization could achieve when bureaucratic obstacles were removed and clear priorities were established. Fisher Body and Chrysler, and the other Sherman manufacturers, had prototype wet stowage installations completed by mid-February, had worked out production processes by early March, and had first wet stowage Shermans rolling off assembly lines in mid-March, barely 3 months after Cole's initial presentation to Barnes and 6 months after his first concept sketches. The implementation wasn't without complications, because retooling production lines while maintaining output targets required careful choreography, where manufacturers gradually introduced wet stowage components into existing production flows, rather than shutting down lines completely for conversion, which meant there was transitional period where some Shermans were being built with partial wet stowage protection or with temporary expedients that would later be upgraded to full specification. The retrofit kit program faced even greater challenges because field modification of tanks required technical documentation and training for maintenance personnel who would perform the installations, and required shipping thousands of retrofit kits to units scattered across the Mediterranean theater and to England where invasion forces were assembling, all while those units were actively engaged in combat operations or intensive training that couldn't be interrupted for extended maintenance periods. The solution involved prioritizing retrofit installations during planned maintenance cycles and accepting that full fleet conversion would take months, with units receiving wet stowage, Shermans gradually as older tanks were rotated out of service for overhaul or as new production tanks arrived to replace combat losses. The combat debut of wet stowage Shermans came in Italy in April and May 1944, when small numbers of the new tanks were rushed to units that had suffered particularly heavy casualties, and the results were immediately apparent to crews who'd been fighting in standard Shermans for months and who'd developed fatalistic attitudes about their chances of surviving if their tank took a penetrating hit. Sergeant James Mitchell of the 1st Armored Division had survived 2 tanks burning under him during the fighting at Anzio, had suffered burns on his hands and face escaping the second vehicle, and had requested transfer to infantry rather than continue serving in tanks, where he believed survival was just a matter of time before his luck ran out. When his unit received wet stowage Shermans in late April, Mitchell initially didn't believe the new tanks would make significant difference because he'd seen too many burn to trust that any modification could prevent fires. But after his new tank took a penetrating hit from a German Pak-40 anti-tank gun that would certainly have ignited ammunition in his previous vehicles, and instead resulted in no fire and no casualties beyond 1 man with minor fragment wounds, Mitchell became evangelical advocate for wet stowage and wrote home to his wife that maybe he would survive the war after all because the new tanks gave crews fighting chance. After-action reports from Italy documented that wet stowage Shermans hit by German anti-tank weapons burned at rates around 15 to 18%, compared to 75 to 80% for older models, and crucially, the fires that did occur in wet stowage tanks tended to develop more slowly, giving crews additional seconds to evacuate. That often meant the difference between surviving with burns and dying trapped in the inferno. Tank crews began requesting transfers to units equipped with wet stowage Shermans, and unit commanders reported improved morale and more aggressive tactical behavior because crews felt they had reasonable chance of survival even if their tank was hit, which paradoxically made them more willing to accept tactical risks that increased mission success rates. The psychological impact was as important as the statistical improvement in survival rates, because tankers who'd been operating under assumption that any penetrating hit meant probable death could now calculate odds more rationally and could focus on tactical execution rather than on managing fear that paralyzed decision-making in combat stress situations. Lieutenant Robert Hayes commanded a tank platoon in the 2nd Armored Division and reported that before wet stowage, his crews had been reluctant to advance into positions where they might draw German anti-tank fire, had developed tactical caution that sometimes bordered on paralysis, because survival instinct overwhelmed training and discipline. But after receiving wet stowage tanks in May 1944, his platoon executed aggressive maneuvers that had been impossible earlier, because crews now believed they could survive mistakes or bad luck, rather than having every tactical error or unlucky moment become death sentence. By June 6, 1944, when Operation Overlord launched the invasion of Normandy, approximately 20% of Shermans landing in France had wet stowage, with remaining 80% being older production, models that would be gradually replaced as they were destroyed or wore out, and as new production caught up with demand. The Normandy fighting provided the ultimate test of wet stowage effectiveness because the hedgerow terrain of Normandy created close-range engagement conditions that favored German defensive tactics and their superior anti-tank guns, creating an environment where Shermans were taking unprecedented numbers of hits and where any design weakness would be ruthlessly exploited by experienced German tank and anti-tank gun crews who'd spent years perfecting their craft against Soviet armor on the Eastern Front. Combat analysis from Normandy confirmed the Italian results. Wet stowage Shermans had ammunition fire rates around 15%, while standard Shermans continued burning at 75% rates, and the difference translated directly into casualty statistics, with crews in wet stowage tanks having survival rates approximately 4 times higher than crews in older models when their tanks took penetrating hits. The improvement wasn't perfect and didn't eliminate Sherman vulnerability to German guns that could penetrate American armor at ranges where return fire was ineffective, but it transformed a near-certain death sentence into a survivable situation where crew training and quick reaction could save lives, and that transformation mattered enormously to the men fighting inside those tanks, who understood their odds had shifted from catastrophic to merely dangerous. Captain William Crawford commanded a tank company in the 3rd Armored Division during the breakout from Normandy in July 1944, and his after-action reports documented that his company lost 11 Shermans to German fire during 2 weeks of intense combat. But of those 11, only 2 resulted in total crew casualties, with remaining 9 producing survivors, because wet stowage prevented catastrophic fires that would have killed everyone inside. Crawford calculated that wet stowage had saved approximately 35 lives in his company alone during that 2-week period, and extrapolating across the multiple armored divisions fighting in Normandy suggested the modification was saving hundreds of lives weekly during periods of intense combat. The broader significance of Cole's wet stowage innovation extended beyond the immediate tactical impact because it demonstrated institutional lessons about military innovation that remained relevant through subsequent decades of American defense development. The fact that a mid-level civilian engineer had to work without authorization for 2 months to develop a solution that Army ordnance had rejected illustrated the dangers of bureaucratic rigidity that prioritized production schedules and existing doctrine over combat, effectiveness and crew survival, and suggested that military procurement systems needed better mechanisms for rapidly evaluating and implementing field-generated innovations that might not fit neatly into established development processes. The speed with which wet stowage went from concept to combat deployment once senior leadership committed to it demonstrated that American industrial capacity could accomplish remarkable feats when properly motivated and when bureaucratic obstacles were removed, suggesting that production delays used to justify not implementing improvements were often excuses for institutional inertia rather than genuine technical constraints. The casualty reduction achieved by wet stowage raised uncomfortable questions about how many American tankers had died unnecessarily in the months between when Cole first proposed his design and when it was finally approved, and whether different decision-making processes might have saved hundreds or thousands of lives by implementing the improvement earlier, even if it meant accepting some production delays. Military historians later calculated that if wet stowage had been implemented 6 months earlier, beginning in October 1943 rather than April 1944, approximately 800 to 1,000 American tanker lives would have been saved based on casualty rates during that period, and the percentage of tanks that could have been equipped with the system, which translated into roughly 3 full tank battalions worth of experienced personnel, who died in fires that improved ammunition protection would have prevented. Harold Cole received the War Department's Civilian Service Medal in 1945 for his contribution to armored vehicle survivability, but he rarely spoke publicly about his role in developing wet stowage, and in interviews conducted decades later, he expressed ambivalence about recognition because he couldn't forget that his design had been rejected twice before circumstances forced reconsideration, and that men had died in that interim who might have survived if the Army had acted faster. He continued working for General Motors after the war, eventually becoming chief engineer for Fisher Body Division, supervised development of numerous vehicle innovations, including improved crash safety systems that applied lessons from military vehicle protection to civilian automobiles. Retired in 1965 and died in 1978 at age 76, his obituaries mentioning his wartime contribution, but not capturing the full story of how his persistence overcame institutional resistance to create innovation that saved thousands of lives. Major Thomas Doane survived the war, remained in the Army, eventually retired as colonel, and in oral history interviews conducted in the 1970s he identified Cole's wet stowage design as single most important improvement to American armored vehicles during World War II, measured by lives saved per unit of effort invested, and expressed regret that he hadn't pushed harder to overcome the initial rejection of Cole's concept, which might have accelerated implementation and saved additional lives. Major General Gladian Barnes went on to oversee numerous other ordnance developments, including improved tank destroyers and artillery systems, but he apparently never forgot the lesson of how close the army came to missing a crucial innovation because institutional processes weren't designed to seriously consider proposals from outside normal channels. And in post-war writings, he advocated for more flexible procurement systems that could rapidly evaluate and implement promising technologies regardless of their institutional origin. Barnes particularly emphasized the need for senior leaders to maintain direct communication channels with engineers and field personnel who might identify solutions that intermediate bureaucracy would filter out as impractical or inconvenient, arguing that hierarchical organizations naturally developed risk-averse decision-making that favored incremental improvements over radical innovations, even when radical solutions were exactly what combat situations demanded. The Sherman tank itself continued evolution through the war's end, with numerous additional improvements, including better armor, more powerful guns, and enhanced mobility, and wet stowage became standard feature of all subsequent American tank designs, with variations of Cole's basic concept appearing in every American armored vehicle through the present day. Modern main battle tanks like the M1 Abrams use sophisticated ammunition storage, systems that isolate propellant and projectiles in armored D, compartments with blowout panels that direct explosion force away from crew if ammunition is hit, representing evolutionary development of principles Cole first implemented in practical form in that Aberdeen prototype during winter of 1943-1944. The story of how one engineer's rejected design made the Sherman practically bulletproof, or at least made it survivable enough that crews could fight effectively without accepting near-certain death if hit, ultimately represents both American military innovation at its best, when problems were recognized and solutions were implemented quickly, and American military bureaucracy at its worst, when institutional inertia and production priorities delayed critical improvements until casualties became politically unacceptable, teaching lessons about balancing combat effectiveness against production efficiency that military procurement systems continue wrestling with whenever new threats emerge that existing designs weren't optimized to counter, demonstrating that even in most technologically advanced military and world, human factors like individual persistence and leadership, willingness to challenge established procedures often determine whether innovations that could save lives are implemented in time to matter or are delayed until after. Unnecessary casualties have already occurred,